Have you ever stopped to wonder why nothing in the universe seems able to outrun light? This idea appears everywhere, in science classes, in movies, in conversations about space and time. But behind this famous limit, there is a surprising amount of confusion. Many people repeat the statement without truly understanding what it means, where it comes from, or what it does and does not forbid. Richard Feynman had a rare talent for cutting through this confusion and revealing what is really going on beneath the surface. Today, we are going to follow his way of thinking and uncover why the speed of light holds such a special place in our understanding of reality. Before we dive deeper, take a moment to subscribe to the channel, leave a like, and write a comment sharing what you think limits speed in the universe. Your interaction helps this conversation reach more curious minds like yours. When people hear that nothing can go faster than light, they often imagine light as some kind of cosmic police officer, actively stopping objects from accelerating beyond a certain point. Feynman would smile at this picture, because it already hints at a misunderstanding. Light is not acting as a barrier in the usual sense. The real story is far more subtle and far more beautiful. Feynman liked to begin with questions that seem simple. What do we actually mean by speed? Speed is distance divided by time. That sounds straightforward until we realize that both distance and time are not as absolute as we once believed. Classical physics assumed that everyone, everywhere, agreed on how much time had passed and how far something had traveled. But experiments showed cracks in this assumption, and light was right at the center of the problem. Light behaves in a very strange way. No matter how fast you move, light always seems to move away from you at the same speed. If you chase a beam of light, common sense suggests you should measure it as moving slower relative to you. Yet experiments stubbornly showed that this never happens. Light always keeps the same speed regardless of the motion of the observer. Feynman emphasized that this is not a matter of opinion or theory preference. It is an experimental fact. Once you accept this fact, the universe demands a price. Space and time must adjust themselves to preserve the speed of light. Time can slow down. Lengths can shrink. Events that seem simultaneous to one observer may not be simultaneous to another. These are not optical illusions or measurement errors. They are real features of how the universe is built. Feynman stressed that the laws of nature are not obligated to match human intuition. Now here is where confusion often enters. People hear that objects gain mass as they move faster, or that infinite energy is required to reach the speed of light, and they imagine some mechanical resistance pushing back harder and harder. Feynman warned against taking these explanations too literally. They are ways of describing the mathematics, not physical forces acting like invisible hands. The deeper reason nothing outruns light is not that the universe forbids speed out of stubbornness. It is that the structure of space-time itself makes the question meaningless beyond a certain point. Asking what happens when something goes faster than light is like asking what lies north of the North Pole. The question assumes a framework that no longer applies. Feynman also pointed out an important distinction that many people miss. While information, matter, and cause and effect relationships are limited by the speed of light, there are phenomena that can appear to move faster without carrying information. This subtlety often gets lost, leading to exaggerated claims or misunderstandings that science has been broken. Understanding this requires intellectual honesty. Feynman insisted that admitting confusion is not a weakness but a strength. If you do not truly grasp why light sets the ultimate speed, memorizing slogans will not help. Only careful thinking and respect for evidence can guide you forward. As we continue, we will dig deeper into how causality, energy, and the very notion of simultaneity are tied to this cosmic speed limit, and why Feynman believed that clarity on this subject reveals something profound about how nature really works. Feynman liked to say that the most powerful ideas in physics are the ones that force us to give up comfortable assumptions. The speed of light does exactly that. One of the most uncomfortable ideas it introduces is the loss of absolute causality in the way we instinctively imagine it. Cause must come before effect, yes, but before itself becomes a slippery concept when time depends on motion. Imagine two events happening far apart in space. To one observer, event A happens first, then event B. To another observer moving at a different speed, event B may happen first, then event A. This is not philosophical trickery. It falls directly out of how space-time preserves the speed of light. Feynman emphasized that this does not destroy causality, but it reshapes it. Only events that can be connected by signals traveling at or below the speed of light have a fixed cause and effect order. Everything else is not causally linked in the first place. This is where faster-than-light motion becomes dangerous to understanding. If information could travel faster than light, cause and effect could be reversed for some observers. You could receive a message before it was sent. Feynman made it clear that this is not merely strange. It breaks the logical structure that allows physics to make sense at all. The speed of light is not just a speed limit. It is the glue that holds causality together. Another source of confusion comes from energy. People often hear that as an object accelerates, it requires more and more energy, approaching infinity as it nears the speed of light. This leads to the idea that engines simply are not powerful enough. Feynman cautioned against interpreting this as a practical engineering problem. It is not about stronger fuel or better technology. The equations are telling us something deeper. The closer you get to the speed of light, the less additional speed you gain from adding energy. From the object's own perspective, something even stranger happens. It never experiences itself reaching the speed of light. Time for the object slows relative to the outside world. But from its point of view, time flows normally. There is no moment where it says, "Now I am almost light speed." Feynman loved this aspect because it shows how misleading everyday language can be when applied to extreme situations. He also addressed a common mistake, treating light as if it were an ordinary object that just happens to be very fast. Light does not have a rest frame. There is no valid way to ask what light experiences as time passes, because time for light does not pass at all in the way it does for massive objects. Trying to imagine riding alongside a photon leads to contradictions, not because imagination is weak, but because the question itself is flawed. Feynman believed that many confusions survive because people want comforting metaphors instead of precise thinking. Saying nothing can outrun light is easy. Understanding why requires accepting that reality is not built to satisfy intuition. The universe is consistent, not convenient. He often reminded students that physics is not about knowing the right words, but about knowing what happens. If someone claims a discovery that breaks the light speed limit, the correct response is not immediate belief or rejection, but careful examination. Does it transmit information? Does it preserve causality? Does it fit with experimental evidence? These questions matter more than dramatic headlines. As the discussion moves forward, the focus shifts to how Feynman used simple thought experiments and everyday reasoning to dissolve the mystery, showing that once the fog of confusion clears, the speed of light stops looking like an arbitrary rule and starts looking like an inevitable feature of a deeply coherent universe. Feynman had a gift for stripping ideas down to their bones, and when he talked about the speed of light, he often returned to measurement itself. How do we actually know how fast something is moving? We need clocks and rulers, but clocks depend on processes, and rulers depend on physical objects, and both are governed by the same laws of nature that light obeys. This is not an accident. The limit imposed by light is woven into the tools we use to describe reality. He pointed out that whenever we try to synchronize clocks at different locations, we must use signals. In practice, those signals are electromagnetic, which means they travel at the speed of light. The very definition of simultaneous events relies on light. Once you see this, the idea of exceeding the speed of light begins to unravel. You would be trying to outrun the mechanism that defines time order itself. Feynman also addressed why this limit feels so unsatisfying to many people. Human experience takes place at speeds that are tiny compared to the speed of light. In everyday life, time seems absolute. Distances seem fixed, and cause always clearly precedes effect. Relativity hides in the background, invisible. When physics reveals that these assumptions break down, the mind resists. It feels like a trick, even though it is simply nature revealing a deeper layer. Another source of confusion comes from astronomy and cosmology. People hear that distant galaxies are moving away from us faster than the speed of light and conclude that the rule has been broken. Feynman would carefully separate motion through space from the expansion of space itself. No object is locally outrunning light. Instead, space between distant regions is stretching. This distinction matters because it preserves causality and keeps the underlying structure intact. He was equally skeptical of claims involving shortcuts through space, hidden dimensions, or speculative particles that allegedly bypass the light speed limit. Feynman never dismissed ideas simply because they sounded strange, but he demanded clarity. What exactly is moving? What information is being transmitted? What observable effect proves the claim? Without clear answers, impressive language becomes a substitute for understanding. What made Feynman especially effective was his insistence that confusion is often self-inflicted. People mix different explanations, metaphors, and equations without realizing they belong to different conceptual frameworks. One moment they talk about relativistic mass, the next about space-time geometry, then about energy barriers, as if all were independent reasons. Feynman would say they are all different ways of describing the same underlying fact. That fact is this: the universe has a built-in conversion rate between space and time, and that rate is the speed of light. You cannot change one without affecting the other. Trying to exceed the speed of light is not like breaking a speed limit on a road. It is like trying to draw a square circle. The rules that define the situation collapse. Feynman believed that when people truly grasp this, something liberating happens. The frustration fades, replaced by admiration. The speed of light stops being a frustrating wall and becomes a window into the elegance of nature. It reveals a universe that is not chaotic but astonishingly well organized. As we move toward the final part, the remaining confusion will be addressed by looking at why this idea, once understood, is not restrictive at all, and how Feynman saw it as an invitation to deeper curiosity rather than a boundary that shuts inquiry down. Feynman rejected the notion that the speed of light limits human imagination or scientific progress. On the contrary, he saw it as a guidepost. Once you understand what cannot happen, you are free to focus on what can. The universe is not smaller because of this limit. It is more intelligible. Constraints are what give structure meaning. He often reminded his audience that physics advances not by wishing the universe were different, but by listening carefully to what experiments tell us. The speed of light emerged from observation, not from aesthetic preference. Every test that probed deeper into nature reinforced the same conclusion. When reality speaks so consistently, the honest response is not disappointment, but respect. Feynman also emphasized the joy hidden in this understanding. Knowing that time can stretch, that space can bend, and that light quietly defines the relationship between them does not diminish wonder. It multiplies it. The fact that such an abstract idea can be tested, measured, and confirmed is one of the great triumphs of human curiosity. For him, the real danger was not that nothing outruns light, but that people stop asking why. Accepting slogans without comprehension leads to shallow knowledge. Feynman warned that false clarity is worse than confusion because it blocks further questioning. True understanding always leaves room for doubt, exploration, and refinement. He encouraged learners to approach physics the same way they approach a puzzle, not a commandment. If someone claims to have bypassed the speed of light, the response should be excitement paired with skepticism. Show me the evidence. Show me the mechanism. Show me how causality survives. This attitude is not negativity, it is intellectual integrity. In this sense, the speed of light is not an obstacle, but a teacher. It teaches us that nature has an internal logic, and that our role is to discover it, not rewrite it. It teaches humility, because no amount of desire can override experimental fact. And it teaches creativity, because working within deep principles has led to technologies and insights that once seemed impossible. Feynman's legacy is not a list of formulas, but a way of thinking. He showed that understanding something deeply enough to explain it simply is the real measure of knowledge. When the confusion around the speed of light dissolves, what remains is not a wall, but a coherent picture of a universe that makes sense on its own terms. The idea that nothing outruns light then stops feeling restrictive and starts feeling inevitable, not because we are forbidden to go faster, but because speed, time, and causality are inseparable threads of the same fabric. Pull one too hard, and the entire pattern unravels. In the end, Feynman would likely smile and say that the most important lesson is not about light at all. It is about honesty, curiosity, and the courage to admit when we do not yet understand. That attitude, more than any equation, is what keeps science alive and endlessly fascinating.